Good morning, ladies and gentlemen. Welcome to the lecture about TESS mission, which will be given by András from the Concoli Observatory from Budapest in Hungary. He is the guy who participated on the data processing pipelines of the TESS mission. So he's the guy who knows really a lot about this satellite. So please welcome András Pál. It's yours, András.
Okay, thank you very much for the introduction. So I think if anyone has some question, I don't know how did you do earlier, but if you have any questions, just type in the chat and there is a chance that I can read it. So I think that's the easiest way at this moment. So let's start and we will see. So in the next well, a little bit more than 1 hour, I would like to give some short summary about the TESS, the satellite itself. So what kind of instrument is it? What can we expect for this? What kind of... so I would like mostly focus on the instrument itself. So this part. And on Tuesday morning, Tuesday morning, there will be a little bit more detailed presentation about some interesting issues about the data reduction. So this slide just summarizes some satellite and ground-based mission related to exoplanets. So as you can see, there are instruments here like Kepler, TESS, or Cheops or Plato, which are designed for exoplanet studies. And there are many instruments here which are generic observatories like Hubble Space Telescope, Spitzer Space Telescope, JWST, GAIA, and other instruments which are not designed for exoplanet missions, but these instruments can provide or will provide the most amount of data related to exoplanet science. So basically, this instrument, TESS itself, was designed for discovering transiting exosolar planets. So all of the aspects of the instrument were driven by this scientific goal, basically. So if we want to understand the basic characteristics of the instrument, then we will see that this type of data collection method, what TESS do, is useful for this science. And then we will learn later on, or we can later on, what kind of other scientific topics can be covered by TESS. So now I would like to show a few slides about TESS, the instrument itself, and then I will just switch screens and I would like to show some sort of typical process data for TESS. And the second half of this presentation will be a little bit more interactive. So sorry for any jitter, but I think that will work. So as far as I said a minute ago, there are missions, space missions, which are designed for exoplanetary science. And there are missions which are just widely utilized for doing exoplanet stuff. And there will be future missions. Well, Cheops is not a future mission anymore because it had launched a few months ago, the end of the previous year. So these missions wouldn't be used as a kind of discovery engine, but these missions are, the primary goal is to do follow-up science. And of course, the scientific yield of all of these missions could go beyond exosolar planets. So just to briefly summarize the most important characteristic of the instrument, it can be summarized in just this one slide, basically. So there are 4 cameras, 4 CCDs per camera, and 4 output channels per CCD. So it's easy to remember because everything is 4. And the field of view is 4 times 24 by 24 degrees, but we will see that this type of field of view is a little bit non-trivial in many aspects, but otherwise it's very easy to deal with it. So because of this setup, the resolution is not so good. So the resolution is around 21 pixel, arcseconds per pixel, which is big. So the normal single limited telescopes, which we are used to use in ground-based instrumentation, mainly is limited by the ceiling, and the rule of thumb number is 1 arcsecond per pixel. So some of the instruments are a little bit better, some of the instruments are a little bit worse in terms of resolution. But compared to all of these instruments, TESS is very low resolution instrument. And from these numbers, we can just compute that the imaging resolution for one CCD is around 2K by 2K. And it's very interesting that this passband of TESS is very close to GAIA RP band, which is between 600 nanometer and 1 micron, which means that GAIA RP photometry can easily be used as a kind of 0 point for TESS photometry, which is very important in the data reduction. And the difference, or I would say root mean square difference between the two instruments is order of hundreds of a magnitude. So it's really, really close. Oh, sorry, it's my fault. Okay, so this is the payload, and the satellite platform is a very simplistic instrument in a way that the main goal of the platform is to provide very good stability in terms of pointing precision, which is attained by 4 reaction wheels and hydrazine thrusters for momentum unloading. And because of TESS uses hydrazine for momentum unload, it has a limited lifetime, but in total there is a huge amount of fuel on board on TESS that TESS could operate up to 20, 30, 40 years, which is a quite good thing, that without any kind of further change in the mission operation, it can be operated until several decades. So yes, so this is a cross section of the TESS camera. It is a wide field lens system. There are 7 lenses, which imply 14 surfaces in total, because each of the lenses has 2 surfaces, and 2 of the surfaces are aspherical. So in some sense, it's a little bit complex optics, but with this optics, we can, or the TESS engineers could obtain very good F number for TESS. And as you cannot see in this image, that the materials for the 7 glasses are different. So there are no, and it implies that the PSF, the point functions, doesn't really depend on the wavelengths, and it's also good because it can also compensate the thermal properties of the instrument itself. And at the bottom here, this is the so-called focal plane electronics into which the CCDs are mounted. This one, and this is the electronics itself, and it's connected via cables. So these are the CCDs. These are 4 CCDs for each camera, and half of the CCDs are covered, so only this part is illuminated, and this part here, this one, and this part, used for storing the frames during readout, which means that the duty cycle of TESS is around 100%. So except for the frame transfer phase, it can collect photons all the time, which is good. This is a photo of mine from the focal plane electronics from the lab, how the 4 CCDs are connected, and the readout channels can also be seen here. This is the lab where the electronics of TESS were designed. And this is a clean room in the black background where the prototype electronics and the flight electronics were connected to the cameras and put it in a vacuum chamber so it can be used for tests. So if we add the lens hood to this system, we will get something like this. So the aperture is around 10 centimeters. The field of view is again 24 by 24 centimeters. And this lens hood decreases the amount of stray light. And as we will see later on, stray light is an important issue about TESS because TESS orbit Earth in a wider orbit. So let's discuss it a little bit later on. This is a photo of the TESS platform. Here you can see the antenna, the high gain antenna, and here one of the most important parts of the TESS payload are the reaction wheels. So the reaction wheels allow us or the engineers to make a very, very good pointing stability, which means that the overall pointing stability is around thousands of a pixel. So it's indeed very good. And of course, it's redundant because of the operations. You need only 3 reaction wheels, but there are 4. So if there is a failure, then the satellite can still operate. So just think about Kepler and K2. The history of Kepler and K2 started at the same way. So Kepler had 4 reaction wheels, then one of the 4 reaction wheels failed, and then the second one also failed, and then the engineers start to operate the so-called K2 mission with reduced number of reaction wheels, which implied that the pointing stability was much more, I would say, lower for the K2 mission. So let's talk a little bit about the satellite orbit, which also drives the data acquisition cycles of TESS. So the satellite orbit is something which is called TESS orbit because it is in 1 to 2 beam motion resonance with the moon, which means that the orbital period is 13, 14 days, between 13 and 40 days. On average, it's 13.7, so it's not 13.5. It's a high eccentricity, high inclination orbit. And because of this 1 to 2 resonance, this orbit is stable for several decades. So without any kind of active station keeping, TESS could go and do observations for several decades, which is comparable to the total expected amount of hydrazine fuel on board, which is used just for momentum unloading. So the satellite telemetry is also limits the data acquisition cycle. It uses K-band, and there is one downlink block for each orbit, which means that using this period of a few hours about a data rate of 100 megabit per second, we are able to retrieve roughly 16 times 600-700 full frame images plus tens of thousands of positive stamps, and we will see later on what does it mean. So this type of data products are associated with TESS at present moment. So we will see that what can we do with this type of data and how it is collected on board. So this is the orbit of TESS. So this figure shows the orbit on scale. So this is Earth. Sorry, this is Earth here. This is here the orbit of the Moon, and this high inclination, high eccentricity orbit was done by the Moon itself, by a lunar flyby, and this type of orbital insertion minimized the need of fuel. And although it's a high eccentricity orbit, the perignon distance, this distance is also in the order of 100,000 kilometers, which means that it's still far away, so still much more higher than the geostationary orbit, for instance. And at the farthest point, it reaches almost the orbit of the Moon. So it's a really wide orbit, which means that and because of the second law of Kepler, TESS orbits this section of this trajectory quite slowly, which means that most of the mission is far from Earth and also far from Moon. So we will see its implication later on about the stray light. So because of this high field of view, wide field of view, it's not so obvious to answer such questions that where does TESS look? Because it's really a three-dimensional spherical problem. So because if you just think about normal, I would say normal telescopes like ground-based telescopes or HST, there is a preferred pointing which you can define by array and deck, and you don't really care about anything else. Here in TESS, you can also define a kind of boresight pointing. We will see later on what does it mean. But it is interesting that the nominal pointing, there is no sky image. So this pointing is just between two TESS cameras, and all of the four cameras point to somewhere else, and this somewhere else means that this somewhere else means that it also depends on the roll angle of the spacecraft. So there are three numbers basically: array, deck, and the roll angle that you have to define when you talk about, okay, please tell me which part of the sky is observed by TESS. So you need basically a little bit more complicated mathematics to compute even to answer such question that is my favorite star observed by TESS, or was it observed, or will it be observed? So instead of the classical spherical geometry, you need to do a little bit more complicated computations, but there are formulae and there are websites which are not so good, but works at some level. I always get questions that why my favorite star wasn't observed by TESS, because that official NASA website say that it was observed, but yes, it was observed, but it fell between the gaps of the CCD, so it's not so trivial to compute, but yes. And what is important that we should also know these vectors, so the vectors between TESS and Earth and TESS and Moon, and we will see later on what does it mean. Okay, so here is a nice view about TESS and its field of view. And if you just put the four cameras together, you will get something like this. So this is the cross-section of the field of view. And this is an interesting image that how would light goes into TESS cameras. But of course, you don't see such beams leaving from the cameras, but you see or the light is entering the cameras. So let's go. And if we are talking about TESS, we need to introduce some sort of special terms which are used by the TESS community, and anyone who deals with TESS data will learn sooner or later what does these expressions or what does these definitions mean. So one orbit is one orbit of TESS around Earth. So it's 3.5 days long. It can be slightly shorter or longer because of the perturbations. But as far as I told, these perturbations are averaged out on a longer time scale, which means that the orbit itself is stable for several decades. So we don't have to worry. But you shouldn't be surprised when one of the data series is just 25 days long and the other data series is almost 30 days long. This is because of this type of, I would say, local or short-term perturbations of the orbit of TESS because of the Moon and the Sun. And one TESS sector is built from two TESS orbits. And if we are talking about TESS observations, we just identify the observation run by sector number. So for instance, the first observation run started almost exactly 2 years ago. It's called Sector 1. Now data are available until Sector 26. Sector 27 has been completed, and now Sector 28 is under observation. So if you just pop up any website related to current status of the test mission, you will see something like this, some numbers and identifications like this. So the primary mission is also ended a few weeks ago, basically. And it is very interesting that the schedule of the summer school is perfect in the sense that I was able to retrieve and pre-process the primary mission data just yesterday, because the data became available on Friday evening local time, which means that you need a few hours to download everything, and then you need a few hours to process everything, and then you have to set. So there is no backlog in terms of data processing, which is good. So how does the pointing of test is defined? So there are 4 cameras. Camera 4 is always centered at the ecliptic poles, and camera 1 is close to the ecliptic as possible. And in the middle of a sector, test looks away from the sun. And if you just consider these definitions, these are 3 constraints: that camera 4 always centers at the ecliptic poles, camera 1 is as close as the elliptic as possible, and test looks away from the sun in the middle of the sector, which is the gap between orbit 1 and orbit 2, so the first and the second orbit of the given sector, which means that the data are downlinked at that few hours of gap. Okay, so we have 3 constraints, and as I told a few minutes ago, the pointing of tests is defined by 3 numbers: array, deck, and roll. And these 3 constraints unambiguously defines us where test looks. So even it is important that even if the test mission operations or mission center or NASA or whatever agency doesn't say anything about the future of the test pointing or test pointings, you can compute it, which is good. You don't have to know in advance because test has a clearly defined structure. Probably it will be changed in the 5th year of the mission when there is a goal to observe the ecliptic plane itself. Because of why? Because of the primary mission design looks like this. So these are the sectors. This is the ecliptic pole, and this is the southern ecliptic pole. This is one sector on the sky. And these are the pointings of the 4 cameras. So sector 1 started here, up to sector 13, and then sector 14, 15 in the other hemisphere. So this is a kind of coverage map, because as you can clearly see, the camera 4 always looks towards the ecliptic poles, which means that it's observed continuously almost for a year, besides the small gaps between CCDs. And if we just project these sectors to the sky in another view and compare with the field of view of Kepler, we will see something like this. So this one here is the field of view of the primary Kepler mission. These field of views are the K2 field of views, and everything else with the shades of blue are the field of view of TESS. And there are the small gaps which are not observed either by the primary TESS mission and K2 as well. So this is why people want TESS to do observation in the ecliptic plane a little bit later on, or as soon as possible, depending on the science. And if we want to be a little bit more accurate and project the field of view in the sky, then we will see something like this. So you can identify the constellations Here is Big Dipper. Here is Orion. Here is the Great Summer Triangle. So you can identify the constellation in the sky, so you can have an insight about the scale of the field of view of TESS. And this was sector 1. Because of these strange projections, you cannot really see at the first glance how does it look like. But if you go further on, this is sector 2, sector 3, sector 4, sector 5. So now you can see that how did the primary mission run in the first year, sector 6, sector 7, etc. 8, 9, 10, 11, 12, 13. And if we just jump on, okay, I will talk a little bit later about the second year and the problems in the second year. Okay, so let's talk a little bit about the data acquisition. So we know the pointing of TESS. We know that it has a very, very large field of view. So in total, if we just sum up everything, we get that the field of view of TESS is around 650 square degrees. And the total per camera, 650 square degrees, which means that if you just multiply it by 4, you will get a number something like 2,800, which is almost something like 7% of the sky. So 7% of the sky is continuously monitored by TESS, and using this data acquisition principles. So basically, the elementary readout or elementary frame is as short as 2 seconds. So it's very, very short integration time. And what is the advantage of very, very short integration time? Means that you can observe quite bright stars as well, because in 2 seconds, the saturation, in 2 seconds long integration time, the saturation limit of TESS is equivalent to a magnitude of 5, 6, 7, depending on the location of the sky, location within the field of view because of the lens, and depend also the color of the star, because TESS has a relatively far red or near infrared passband, so between 600 and 1000 nanometers. So it depends on the color of the star, but the rule of thumb is something like 5, 6, 7 magnitudes. Of course, if you define it with respect to the GAIA RP band, it's much more better, much more easier to deal with. So elementary readout is 2 seconds long, and these frames are stacked. And there are, I would say, 2 or 3 stages of stacking the stamps. In first stage, 10 frames, 10 frames are stacked in a way that the pixels with the lowest and highest values are rejected. This implies a very interesting feature, that because of this very interesting consequence, that because of this stacking and this type of stacking, so you just drop the smallest and highest value of the 10 pixels within 20 seconds, you can easily get rid of the cosmic hits, because cosmic rays hit the CCDs, and it can be quite prominent. Just think about the Kepler frames, and with very, very simple onboard data acquisition algorithm, you can easily get rid of the cosmic hits. So the shortest exposure time that is capable to do with TESS is 20 seconds. And these 20 seconds frames are also stacked. And there are 2 types of images at this moment, which is retrieved. So we take roughly, or not roughly, exactly 90 of these 20 seconds long elementary frames. We stack it, and we get something which is called full frame images. but the total exposure time or the net exposure time of the full frame image is 30 minutes, which means that the cadence is also 30 minutes. So we cannot really see short variation, so variation with very short time scales. And because of the primary science goal to discover and characterize transiting exosolar planets, the engineers included 2-minute exposures as well, where only only six of these elementary frames are stacked. But here, not the full frame is download, but only pre-selected stars. So in this mode, TESS looks or works almost same the way as Kepler do with the long cadence frames, which is good. And then people can just analyze timescales which are shorter than half an hour, which is good. And theoretically, TESS can do in the future even shorter cadences, even can go up to or down to 20 seconds. So people who are doing astroseismology are quite interested in this type of data acquisition. And this whole issue, what I'm just showing here, depends on the available bandwidth. So as far as I told you, there is a bandwidth limitation and storage limitation, which means that you cannot save everything. And you have to make some sort of compromise. The shorter the cadence, the smaller the total amount of stars what you can observe during a sector or during an orbit. Which means that you really need to carefully justify your targets. And of course, once the targets are justified, then there is a list of pre-selected stars, which is an order of tens of thousands. Then after compression, these can also be retrieved and analyzed. So these are the two basic data products of TESS. And yeah, this is good. So what is the data availability of TESS? So public data releases. There is this MAST portal, this archive of the Space Telescope Science Institute. And the portal itself is optimized for short cadence targets, light curve, and image stems. And it also has some additional features like cutout from full frame images and simulations and search tools. So this is very good, this part, if you are interested in a single star or a few stars, which you can analyze manually. You can just download the data, search for something, do the photometry, and do some analysis, and that's it. But what is even more interesting, that what can we do if we are interested about everything? Bulk downloads. This is a very nice website where you have just a few links where you can find scripts which just download everything for you. Mostly useful for the full frame images. Yes. Including calibrated images and raw images, and the approximate data product, the volume of the data product is 1 terabyte per sector, which is, I would say, it's not a big data volume compared to present-day standards, but you will get this data in every month. So until this, I think in our computers here in this observatory, we downloaded approximately 35, almost 40 terabytes of TESS data, which includes not just the FFIs, because if you just sum up this 1 terabyte with the 26 sectors, it's just 20-something terabytes. But if you add the light curve, the image stems, the short cadence information, it's still bigger. So that's why I was saying that it's the total amount of TESS data product is around 40-50 megabytes. It depends on what do you do with the data. So if you do compression, then it can be smaller, but the access is also slower. So it's also a kind of compromise. How do how do you manage your data. And bulk downloads are important for massive data processing. So if you are not interested in 1 star, 2 stars, or a dozen of stars, but if you want to do photometry on tens of thousands of stars, then the fastest way to do is to download everything and do the processing for yourself, because otherwise it will be slow. And of course, it's essential for moving objects. And I forget to mention here, but it's also important, this type of data product, for transients. So if someone wants to do photometry on supernovae or anything which was not known in advance, I mean, before the allocation of the short cadence data, because of this, you can also you can just use the full frame images. So it's a huge amount of data, and if you want to do efficient test processing, well, you may, or you can combine the both approaches, download a few stars or download everything and start to pick. It's a kind of cherry picking that you just grab what you need. So this was a quick summary about TESS. So I think I was quicker than I expected. And then we have a small amount of time, and I would like to show you some data products in a little bit more interactive way, because I think this is the easiest at this moment. So how does TESS frames look like, basically? So let's start with at the beginning, like sector 1. Yes. So in this directory, there are almost 1,300 frames, and these 1,300 frames show the combined images from the TESS cameras, just starting for sector 1. So this particular frame, what you can see now, is the first public scientific frame series of TESS. As you can see, there are 60 CCDs, but these CCDs are arranged in a little bit tricky way, that this is camera 1, CCD1, camera 1, CCD2, camera 1, CCD3, etc. So it's very easy to identify the camera number and the CCD number, but it's not so easy to identify the orientation with respect to the sky. And this bright saturated something here is because of planet Mars was in the field of view. It happens sometimes. Because TESS avoids ecliptic plane, it's very, very rare that rocky or giant planets will be in the field of view, but because of the inclination of the orbit of Mars is relatively high, and Mars is relatively close, that it could happen that the inclination, or not the inclination, the ecliptic latitude of Mars is larger than plus minus 6 degrees. So that's why it's here. And if we just start to play it as a kind of movie, we see that the frames are changing. And we can clearly see that there are these bright features on the frame, which is because of either of Moon or Earth was in the field of view at some level. Not in the field of view of the cameras, but in the same hemisphere where the TESS cameras look, which means that it will yield a little bit amount of stray light. And if you just go further and further, as TESS orbit Earth, the amount of stray light decreases. So this is a nice image when there is no stray light from sector 1. This is the Great Magellanic Cloud in the southern hemisphere, and this is close to the ecliptic plane, the camera 1. So as you can see, this is something what happens during orbit of TESS. Here, the amount of stray light start to increase, and in some cases, you can get huge amount of stray light. And if you do data processing on any kind of TESS product, like normal stars searching for exoplanets, whatever scientific case is your favorite, you clearly have to deal with this. So you clearly have to do something to distinguish between astrophysical and effects and the stray light. So this is how TESS would look on the sky. This is also a huge amount of stray light here in camera 1. This is because of either Moon or Earth. I don't know, but as you can see, it can be quite prominent. So a few frames are basically not available for any kind of scientific analysis because of this. So this is one type of, I would say, data product that you can retrieve. So this total amount of data, what I just shown here, it's around 600 gigabytes. Not these small images, but the corresponding feeds files, because each of the frames, like this frame here is 2K by 2K, but here is displayed by like, I don't know, 20 or 256 by 266, so 56, so a little bit scaled down. So this is one type of, I would say, data product. And I would like to show you something else, which are also interesting. Let me show you this one. This is a little bit different view of TESS. This is camera 1 on the left. This is camera 4 on the right. Here, the total amount of stray light was so high that this camera is completely off for a few hours at the beginning of the sector. And these are not normal images, but I showed you a few minutes ago, but these are differential images with respect to a given frame. And as you can see, there are many interesting features like this comet. So this comet was in the field of view of TESS, and this is the dust trail of this comet, and this is very interesting. So there are frames which are bad, and you can clearly see the bad frames here. And this frame is bad, or this series of frames are bad because of the momentum unload was performed during this data acquisition cycle, which means that the pointing was not so stable, so you can clearly see that the residual of the stars are bigger. So as you can see, as time goes by, you can see that what's going on in the sky. You see some variability, and you see that this comet here really does something, which is interesting. And this type of frames can be derived quite easily, or more or less easily, if you download everything. You can identify the stray light also. So these are the typical stray light structures using the cameras. And yeah, in these frames, the stray light is very, very prominent. And then a little bit later on, disappears, and so. So if you are analyzing the differences between the frames, you can get basically more information about the characteristics, not just the characteristics of the instrument itself, but about the actual variability. So on Tuesday morning, I would like to show you some sort of, I would say, data processing methods where you can exploit this type of features, or this feature of analyzing the differences between the images. And there are things in these frames which we don't know what are these. This is a kind of like a cirrus cloud here, which moves from the right to the left. So this is also quite interesting to analyze. And I would like also to show you something else. How does this looks like on the sky? So this is a sky chart from sector 19. So this is from the northern hemisphere. As you can see, the Big Dipper is here. The classic Kepler field is somewhere here between Lyrae and Cygnus. This is Cepheus, Cassiopeia, Taurus, Auriga, etc. And here, this dashed line shows the orbit of Moon as viewed from TESS. And if we just jump through these frames, we can see that the orbit of Moon intersects the field of view of TESS, but we are lucky because we don't see the Moon, which is good, which implies that there is no stray light. And if we just speed up a bit, just a moment, we will see, just let me speed up. This is the Moon here. This is the Moon here. And as you can see, if the Moon is close to this field of view, then you will get a huge amount of stray light, basically. And then, if you just look further away, I'm just trying to find Earth in these maps. Okay, probably I picked the wrong sector. So let's check another one. Yeah. In the first image of sector 13, the Moon was literally in the field of view of TESS. So that's why, and that is also an interesting thing, that people start to change a little bit the observing strategy of TESS, because this map here on the right shows the original plan for the first year of the primary mission, and the plan for the second year was roughly the same, just flipped into the northern hemisphere. But it turned out during the mission that the stray light in this part of the sky, which is basically the summer season, a little bit northern from the ecliptic, was affected by Earth and Moon quite significantly, that the mission operation concluded that it would be better to shift the field of view of TESS toward north. And it had a few implications that okay, the stray light was a little bit better than expected, but or than the previous or the original configuration. But on the other hand, this area of the sky was completely avoided. And the problem here that even in the future, because of this 1-to-2 resonance, this part of the sky cannot really be observed efficiently. So probably this part of the sky will be missed by TESS. And even when in the 4th, 5th years of the mission, when people would like to observe the ecliptic plane, it will be the winter ecliptic and not the summer ecliptic because of this, because the stray light in this part of the sky is much more slower. So even when we are just considering that or saying that TESS is a full sky survey, etc., it is not so obvious because of this instrumentation effect. So this is the map of the sky with this sector shifted. And this, if you're just interested in these three numbers, the array, deck, and the roll angle, you can find it, and then you can use it to identify. But the good thing is that the third year of the mission just started a couple of weeks ago with sector 27, and now it joins to sector 28, and now everything is fine again, I would say. So the mission goes in a kind of nominal mode. But the other interesting thing what we will see, I hope that within a few weeks, that the long cadence frames are not anymore 30 minutes long, but now they will be 10 minutes long. So the engineers were capable to increase the performance of the downlink, which means that the total amount of data which is downlink from the tests is roughly twice as big as earlier. And then it means that the cadence of the frames can also be increased. So we will see that what will we get. So yeah, that's what I'd like to show you, and I think I'm perfectly on time. Yeah, something like now. So thank you very much, and let's continue a little bit later on with some aspects of the data processing.
We have time for questions. So if you have any question, please raise your hand by using the emoticons, and I will invite you to ask your question. So far, I cannot see any. But actually, I have one question. András, how do you deal with the straight light? How do you remove it?
It's a very good question. So stray light looks bad, but otherwise it's a smooth structure in, I would say, 90% of the cases. So it's smooth. So it can be modeled by splines or polynomials or something. So it will significantly increase the noise level, of course, because it has shot noise, photon noise. But on the other hand, it is relatively smooth, and you can manage it quite. The problem here, when this amount of stray light is it's not about the amount of stray light, it's about the structure of the stray light. And in some pointings, when the geometry is in a way that the Earth and the Moon is close to I would say, the corners of the Payload or something, that there are very sharp structures. And those sharp structures cannot be removed in an easy way. So I can basically show you some typical examples. I think it's for these last few sectors can be a good example because it's from the Northern survey, and because of this amount of data is higher. I'm just looking for some images. Just a moment. Yeah. I can share it. So for instance here, so this is also stray light here, and this is also stray light here. And here in this is camera 1 CCD2, you can remove it quite easily. But here, because of these sharp structures, or here, this one, it's not so easy to remove or not so easy to deal with. So you always need to find some sort of reference frames which are not affected by stray light at all. You can subtract it. You can model the stray light, and you can subtract the model of the stray light from your original image, and you will get the final product. And besides a few cases, it works quite well, which is good. Because of the optics, the fast optics, the corners of the CCDs, because the optical axis is here, this is the farthest point from the optical axis, this is the most prominent. So this corner, these corners usually should be cut or removed, because it's it's not so easy to deal with at all. So this is something, but otherwise it's okay.
Okay, thanks. So, any other questions? It seems that everyone is satisfied with your talk. Okay, so thank you very much. Thank you very much for your talk. Good luck with your mission in Prague in next days. And we'll see you on Tuesday on the hands-on session. So thanks a lot.
Okay, thank you. Bye.
Bye-bye.